right, last but not least, definitely not least, number 78, it's about force of drag again. Force of drag, as you remember, force of drag formula is 1/2. Then we have rho, density of the fluid. A is the cross-sectional area of the object that is moving through the fluid, times C, which is the drag constant for that particular shape, and all that times V squared at that moment. And V is changing due to drag. That drag equals mass times acceleration. And remember, acceleration, it's decelerating. When I write this, I should say mass times acceleration is going to be 1/2 rho A C V squared. Acceleration is dv dt. So from there, I can cross multiply. Now, make sure that we realize that our V and our A are opposite each other. So acceleration, so I have my dv over dt equals 1/2 rho A C V squared. And the change of velocity is negative with time. So I need to put a minus in front of this. So then if I cross multiply, forgot am here. So to get my dv over v squared on the left, I should have negative 1/2 rho A C times 1 over mass. So I'm just going to do 1 over m, all of that times dt. So now I'm going to integrate both sides, v to the negative second, and when I integrate that from v0 to vx that I'm after, I should have, so 1 over v0 minus 1 over vx. And that equals, when they integrate it by dt, so I have 1 over v0 minus 1 over vx being negative 1/2. I'm going to put 2m down there. Rho A C times t will be on the right. And that's your first expression because you are integrating this from 0 to t, so that's your top. Then from here, you will have your 1 over vx should be equal to 1 over v0 plus 1 over 2m. I'm just going to do rho A C T. So common denominator is going to be, so we've got 2m plus v0 rho A C T divided by 2m, and v0 will be equal to 1 over vx. So when you flip-flop, your vx from there is going to be 2m v0 over 2m plus v0 rho act. And then see what they did in their original formula. They just took the 2m out, and that's how they end up with vx equals v0 over 1 plus v0 rho act over 2m. That's how they wrote it. We're done with A. We proved it! Over 2m. Everything is there. For B, so since our object is considered a rectangle, so it's traveling like that through, C for rectangle is 0.35. That's just a coefficient. And so we need to figure out if friction is neglected, how long will it take until the car's speed drops from 10 meters per second to 5 meters per second? So it's going to be 1/2 of what it was before. 2 should be equal to 1 plus C rho A V0 T over 2m. So then C rho A V0 T over 2m should be equal to 2 minus 1, 1. From where t is going to be 2m divided by C rho A V0, which is 3,000, this is 2 times mass, divided by, since it's a sideways moving rectangle, C is 0.35, the coefficient, it's all lookup-able, times rho is 1.2, the density of air. Then we have 1.4 times 1.6. Initial velocity was 20. So technically, this comes 150. So I get 150 divided by, in parentheses, 0.35, 1.2, 1.4, 1.6. gets me 159 seconds. 159 seconds. And then to drop to 5, that's 1/4. So I would say this is now equals 1 plus over 2m. So then it's going to be 4 minus, that's 3. So this becomes 6m. So that's 6 times 1500. So then we'll do, we got a 0 out of here, 0 out of here, 3. So it's going to be 450 divided by that whole contraption. So 450 divided by 1.2, 0.35, 1.6, 1.4 in parentheses, 478. 478 seconds. How many sig figs are we allowed? I'll go for 480 seconds, and this would be like 160 then seconds. All right, those are the answers to B. And finally, C. Assess whether or not it is reasonable to neglect kinetic friction. If mu is 0.01 even, that would be 147. So force of friction, 147 newtons, let's say that. Then what is our drag? They are in the same weight category, so we cannot really disregard force of friction, even if it's teeny tiny, because it's very comparable to the force of drag. So the answer is no.